So thanks a lot and welcome back. And I'd like to introduce my colleague Katja Hoffmann, who is a researcher in the Machine Intelligence and Perception group here. And actually the project she's going to talk about, Project Malmo, Chris Bishop already mentioned in his talk yesterday. It's the Minecraft AI platform that we've developed in the course of the last 1.5 years. So Katja is going to give you an introduction. We'll also have a demo this afternoon in the Demo Fest. Okay, there you go.
Thank you very much, Scarlett. Welcome to my talk. I hope you can hear me all right. There you go. The project I will talk about is Project Malmo, as Scarlett mentioned. And I'm the research lead of the project, but there's a large group of people already doing research on this platform, as well as our core development team, Matt Johnson, Tim Hutton, and David Bignell, who is here in the audience today. We also have an amazing set of interns. Our last year's project interns are listed here, and Dilip, who is the current intern, is here in the audience as well. As you probably know, research in artificial intelligence has made enormous progress over the past few years. In fact, the progress was so rapid that even for people in the field, it came as a surprise how quickly the technology has developed and how quickly we have moved to very exciting applications of this new technology. And specifically, I'm talking about deep learning and the progress that has been made there. Some of this progress would have been unthinkable even 5-6 years ago. But today we have deep learning approaches that do state-of-the-art speech recognition that is at the level of human accuracy. And technology like this powers products today already, such as the Skype translator that allows people to have conversations across language barriers while simultaneously translating language from one person to the other. So this is one very exciting application where AI is already helping break down barriers between people and allowing people to communicate with each other. Another example is the progress in deep learning that's been around computer vision. There's now first applications that, for example, help visually impaired people see. Maybe you have seen the Seeing AI project where a blind person can walk around with glasses. They can take a picture of a scene around them and get image captioning to help them interpret the sounds that they see, interpret the world around them. So this is very much about augmenting human capabilities and giving them more power, more control over their environment and better ways of interacting with their environment. With all this dramatic advance in AI, some people have started to speculate how close we are to actually solving AI. Seeing all this rapid progress, it seems that, well, maybe there's just a small step to get to the level of human-level intelligence. But what does that actually mean? And where are we along this quest? I'm arguing here that we're actually very far away from achieving anything that looks like the kind of learning ability that we see in humans or in animals in general. All the examples that I've mentioned and all AI applications at the moment, in fact, are examples of narrow AI. It takes a large team of experts, a large amount of resources to develop each individual application. So for example, in the Seeing AI or in the image captioning work, it would require a number of machine learning experts. We would need large amounts of people who annotate images, who provide labels for those images, and then we can train models, and each individual model is only good at one individual task. So it's a very narrow kind of approach that is very specialized in doing one specific task very, very well. If we compare that to the kind of learning that we see in biological learning, we see a large amount of flexibility, and the greatest amount of flexibility we see, in fact, in human learning. If you compare a newborn child to the current state-of-the-art in AI, a newborn child cannot translate English to French. It can't recognize speech. And they cannot tell you that the person there is a guy on a skateboard. But over the course of our lives, we learn to deal with all the tasks, all the challenges that our environment throws at us. So a child growing up will learn the language of their parents. They will learn the skills, the social skills that allow them to deal effectively with the people around them and to achieve what they want in their life. Now, is there a way to actually move towards that, towards the kind of flexibility we see in biological learning? One important line of work there is reinforcement learning, which is an approach that works towards systems that learn interactively from interaction with their environment. So in the next part of the talk, I want to spend a few minutes in highlighting some of the ideas and some of the insights that have been developed there. Just to give me a brief idea of your background, who in the audience is familiar with bended approaches? Raise your hand. Okay, that's roughly 5%. Who is familiar with, let's say, Q-learning? Okay, also roughly 5%. Okay, so I will spend some time explaining those core ideas because I think they're very important and they will be very important in the future. Starting with bended learning. Bended learning is a type of reinforcement learning. So it's a type of learning approach where systems learn from trial and error to adapt interactively to their environment. In contrast to the full reinforcement learning problem, bendeds make some simplifying assumptions. In particular, they assume that whenever an agent takes an action, that action does not affect the state that it will see in the future. So if we look at learning as an interactive loop, as you see over there, we have an agent. So that could be some system, for example, some character in a computer game. That could be a search engine, an arbitrary system that makes some decision. That agent observes something about the environment. So we can call that context, which is distributed according to some context distribution X. It observes a context. It decides to take an action based on the context that it has observed. That action is then taken in the environment. And in response, the agent observes some kind of reward signal. The name bended comes from the comparison to what happens in casinos. So if you see the one-armed bandits, the slot machines there, you can imagine that you come to a casino and you're told that one of those machines is biased. So one of them has a higher payoff than the other machines. Now, how do you deal with that scenario? You don't know when you start which machine is the one that gives you higher payoff. So you need to try all the machines a certain number of times to understand what the likely payoff function of each of those machines is. But once you have figured out that, oh, this one is likely the one that has a higher payoff than the other ones, then you want to keep playing that machine so that you make a lot of money. This trade-off between trying the different machines or the different arms to gather more information versus playing the one that you think is best to get a likely high payoff is called the exploration-exploitation trade-off. And bended learning, in fact, formalizes this challenge to find a good trade-off between exploration and exploitation. In all of these scenarios, the goal of the agent is to maximize some cumulative reward. So in this scenario here, you could imagine that you want to maximize the long-term payoff that you get from those machines. When we look at bended learning, there are a couple of approaches that are typical for doing this exploration-exploitation trade-off. A very common and very simple type of approach is called epsilon greedy. The idea there is that with some small probability, epsilon, you take a random action. So you pull one of the machine's arms and just uniformly at random. But the rest of the time, you take the action, or you pull the arm, that you think has the highest payoff. And in practice, that simple approach actually works quite well. The problem is that you need to tune that epsilon parameter. So you need to know how exploratory you want to be in order to not spend too much time exploring when you could already be reaping the benefits of what you have learned. Another type of approach is called UCB, and it's a whole class of approaches that are based on the principle of optimism in the face of uncertainty. So the idea there is that when you are uncertain about a machine's payoff, then you would be quite likely, then you would prefer to take that particular action to learn more about its consequences. The idea there is that you give an optimism bonus to each of the actions that you have available. And you can see that there, that this optimism bonus is based on the number of times that you have already played that particular arm. So the more often you play it, the more confident you get that you have a good estimate of the consequences of taking that action. A third approach that I would like to highlight is Thompson sampling, and this is a type of approach that has become very popular over the past few years. The idea there is that instead of just maintaining a point estimate, an estimate of how high the payoff of that particular action is, you maintain a full distribution, the posterior over the reward for a given action. And then using that posterior, you can actually sample from that posterior. And then once you take that sample, you take the action that is optimal according to your current sample. The effect of that is that you very naturally trade off between exploration and exploitation depending on the uncertainty in your estimates. And roughly speaking, you will take an action according to its probability of being optimal, given your current model, given what you already know about the world. And this type of approach is actually quite powerful in practice, and it already allows us to develop systems that can learn interactively in interaction with their environment. There is an extension to multi-opt bandits where you take context into account, but I will skip over the details of this. I just point to some of the resources there in case you want to read up on some of those details. Now, how can we use how a bandit approach is used in practice? One case study that I would like to highlight is restaurant recommendation. And this is work that Philip Wadlinski and I did with our intern, Konstantina, last summer. The idea there is when you come to a new city, you want to figure out where to eat in Cambridge tonight. If you were to ask another person, they would first gather some information. They would try to learn to know you a little bit and maybe see what your preferences are. So for example, you could start a conversation and say, hey, do you know a good restaurant where I could go for dinner tonight? And the other person could say, well, what kind of food do you like? Do you like Italian? Do you like seafood restaurants? So you say Italian. And then based on the information that they gather, they can give you better, more targeted recommendations. We address this problem, or we modeled this kind of problem using a contextual bandit approach. If you are familiar with graphical models, you will see that here we model a user and an item and the affinity between users and items. If you're not familiar with these, don't worry, I'll just talk through the high-level ideas behind this model. So the idea is that we keep track of the model parameters. So in particular, we want to model latent factors that could explain what types of users like what kinds of restaurants. And we infer that from the data, from the observations that we get, and we maintain the full posterior distribution over the user item affinities, so over the probability that a user will like a particular restaurant. Now, when a user comes in, at every point in time, we will have some model of their preferences, some model of how likely they are to like certain restaurants. So we can use Thompson sampling to generate new recommendations for them. So we can propose restaurants according to the posterior probability that that restaurant will actually be liked by the user. So at every point in time, we sample from the model, we present the recommendations to the user, we get some feedback, and then we can immediately update the model. So this allows a recommender that can immediately respond to the new preferences that you provide them. Just to give some idea of the results here, we were able to show that, first of all, this model allows you to very naturally incorporate offline information. So if you have any initial expertise, any initial data, you can start using that to initialize the model. And then from that starting point onwards, you can keep learning as you go along. So you can see on the graph over there that already given some initial information, given some offline data, we get to roughly 60% average precision when we recommend restaurants. But then with each individual question, with each individual point of feedback, the recommendation quality very rapidly increases. So we can very rapidly learn to pick up new preferences as they become available to us. Another quick example that I wanted to highlight is that we can use this kind of technique to optimize online radio. In this particular work here that I did with Ulrich Paquet and Weinan Chan, again last year, we looked at how you could optimize a listening stream for radio listeners. So if you come to an online radio system, you can provide an initial artist, and then the idea is that the radio will play songs that are likely to fit well with that particular artist. We can use two sources of information here. One is offline data, the kind of information that people provided through generating playlists. And we would assume that the kinds of songs that people like are the ones that typically co-occur in playlists. But in addition to that, we want to very specifically optimize for online listening performance. We incorporated that such that we would minimize the number of skips. So when a user fully listens to the song, that is interpreted as a positive signal. When they skip a song, that would be interpreted as a negative signal. So we want to minimize the number of skips that we expect in the user's listening behavior. In this particular paper here, we showed that you can optimize that particular objective, staying close to the offline playlists, but also optimizing for minimum number of skips simultaneously. And just to give an idea of the results here, we show that we, with quite a large margin, improve over just using either one of the data sources, so we can very effectively optimize for online listening behavior. And we also get some very nice embeddings of artists in a latent space where we can see that popular artists tend to be grouped together. So there people tend to, people who listen to one popular artist tend to listen to other popular artists as well. But as the taste of a listener becomes more specialized, they tend to be in a very particular section of that space and not listen to other artists as much. Now, I want to move towards reinforcement learning. So as I mentioned earlier, blended approaches make this crucial assumption that whatever the system shows, whatever action the agent takes, does not affect the future state. And this is a reasonable assumption when we assume that a new user that wants a recommendation is independent of other users that the system has seen in the past. But if you want to model longer-term conversations where the state is maintained throughout the conversation, then that model would not be appropriate. And in that case, we need to move towards full reinforcement learning, where the future states are dependent on the current system actions. One example where this is the case, as I mentioned, is in conversations. So let's say the system takes a turn, maybe a response to a query, response to a request for a recommendation. The user may refine the query. And at some point in the conversation, we can detect whether either the user is abandoning the system in frustration or they have found what they're looking for and they're delighted with the results. Now, this again can be modeled as an interactive learning problem, as I show over there. And now, as I mentioned, in contrast to the bandit problem, we're now in the full reinforcement learning problem where the state, the next state that we observe, depends on the previous state and the previous action. These kinds of reinforcement learning problems can actually be very nicely or very nicely correspond to things like learning to navigate a maze. So if you have an agent that wants to find some, or that needs to find some goal in an environment, we can model this equivalently as a reinforcement learning problem, where the agent has to move through that maze and would only observe feedback when it gets all the way to the end of this maze. In terms of the problem formulation, this would be equivalent to having a conversation with a very late reward in the conversation. And a popular type of approach to solving this is so-called Q learning. The idea in Q learning is that you look at temporal differences between your estimates of how high a reward is going to be, given that you take a certain action in a certain state. And you can see that over here, that we use an iterative approach where your value, the qt plus 1, so this is the value of taking an action t in some state st, is backed up to the old value plus some learning rate, the reward that we observed for taking the action in that particular state, plus the maximum of the maximum value that we can get in the state that we see afterwards. Now, this is fairly abstract, so I just want to illustrate this in a small demo. Now, I was told that it's a bad idea to do live demos. We'll just see how this goes here. All right, that actually seems to be working. Right. So what you see here is a standard reinforcement learning approach called Q-learning that we have implemented in the Malmo platform for AI experimentation that I will talk about in just a few minutes. What you can see here all the way on your left is the state of the world that the agent has seen. So this is the model that the agent is maintaining. And you can see these red areas are the ones where it has already learned that taking that particular action in that particular state is a bad idea. So in this case, it results in burning in lava. For the more neutral states, it has learned that there are no particular bad consequences associated with those particular states. Now, the only observation that the agent gets here is the number of the square that it's on. So it's only observing, hey, I'm on square 53. Now, if I take action forward in 53, that's generally a bad idea. So you can see that the generalization ability of a tabular approach like this is not very high, but it very nicely illustrates this idea of backing up your estimates of the value of taking an action in a particular state. And as the agent explores the environment more, it'll be able to backpropagate to earlier and earlier states that, hey, this is the right path towards the goal. So eventually it's pulled towards the goal, and then it learns to back up those states. And within roughly 150 iterations, it manages to get to the goal very reliably. So I'll keep this running in the background, and we can look back in a few minutes to see whether it's actually managed to find the goal. All right. Right.
Do you measure the generalization of this kind of,
Oh, sorry, can you raise your hand?
How do you measure the generalization of this kind of, algorithms? For example, do you change the environment after he learns something? After he's really successful in this kind of environment.
Right.
You are changing you are like evaluating if he's really powerful when the environment is also like adversarial to him.
Right, that's a very good question. In general, if you use these classic types of approaches, like tabular Q-learning, the generalization ability is not very high. If you have some distribution over environments, then your Q values could approximate the joint distribution over all those environments. But as you probably know, there's a lot of very interesting work at the moment that automatically learns a good representation for a given environment. So for example, if you use visual features and combine reinforcement learning with deep learning, then you can automatically extract a good representation for generalizing across many different environments that have, for example, lava or that have similar visual characteristics. It's very much an ongoing area to understand how to get both very robust learning and this good generalization ability. At the moment, approaches typically do either one. So for example, tabular Q-learning has good learning guarantees, so we know that it will converge to the right or to the optimal solution using quite mild assumptions. And using deep learning, we can get good generalization ability, but it's much harder to get robust performance there. And it's not very well understood what kinds of guarantees we can get over there. But this integration is very much an interesting research area. Oops, we can see whether it's found the goal. Okay, now you can actually see that it's found the goal once. So you see a green, a very positive value over there. But the policy has not fully converged yet. So what's happening now is that as the agent keeps exploring and getting to the goal more and more often, it will more and more reliably get to the goal until it converges to that solution. All right. Were there any other questions at this point? No. Then let's move on. So as was already highlighted here, there's still many interesting questions, for example, around how we can generalize effectively, how we can learn effectively in complex scenarios. And the two examples that I'm showing over here are two agents that we trained to imitate an expert. So we find that if an agent just has to explore randomly, it's actually very slow to learn. It takes a long time before it encounters the goal, and then it takes a very long time before it can actually learn to reliably get to the goal. If instead we provide just a handful of examples of an expert navigating to the goal or demonstrating to the agent what it has to do, then within a very small amount of data, we can actually train the agent to imitate the expert's behavior. And in the examples here, we're actually using the visual features. So the agent is only observing the pixel screen, and it tries to, or the learning approach tries to minimize the KL divergence between the agent's behavior and the demonstrated expert behavior. So it tries to find a policy that is as close as possible to the expert's behavior. And this works very, very rapidly. However, there are many open questions on how to actually learn robustly in those kinds of complex environments that we see, hopefully eventually in the real world, but initially in something like computer games. Just to point out a few open challenges. A key challenge is to learn very general, robust representations that support learning across tasks, for example, in a multitask learning scenario, or that support transfer of knowledge between tasks, in so-called transfer learning, and eventually lifelong learning. So when we think about learning ourselves, these are all very obvious. When we learn one task, when we learn to ride a bicycle, we don't forget how to brush our teeth. But for the current AI approaches, that is very non-obvious. Usually you train an agent to achieve one particular goal, to do one particular task, but it's not yet clear how this can be robustly maintained so that a new skill can be learned and then skills can be retrieved whenever they become relevant in a new scenario. So that's very much an ongoing line of work. Ideally, we would like to be able for the agents to learn generalizable skills. So for example, when you know how to walk around, then you can do a more complex, you can do something more complex. For example, walk to a table and pick something up. And you need to put together different kinds of skills in order to achieve more and more complex goals. Again, that is something that we don't know how to do yet. And it's very much an open challenge of how to approach that. And finally, lifelong learning is the challenge of understanding how an agent can continue to learn new things over the whole course of its lifetime, again, without forgetting, and with becoming better and better at a task as it's practicing it. It is not clear how to learn in environments that change over time. So if you imagine an AI agent that let's say we want to deploy an AI agent that can help their users achieve certain goals. Well, as you go through your life, you will have different goals. So how do you communicate with that agent that it should be doing something else, that it should be learning something new, and that it should use a new skill to actually help you achieve your goals better? And finally, there's a very important question around feedback. So how can AI agents be taught effectively? How can they learn from human feedback, or a combination, for example, of having a user demonstrate a particular task and then providing feedback as the agent goes along and learns to get better and better over time. So this last part of the talk is very much about finding a way to start to answer those questions. And I would like to introduce the Malmo platform, which we have designed to be a platform for AI experimentation, to make these kinds of experiments as easy as possible, to allow us to push towards answering those very fundamental questions that are still very much open and unsolved. Before I move on, who is familiar with Minecraft, let's say? Who has heard about Minecraft? Everyone who has played for more than 2 hours? Okay, that's about half. So if you're not familiar with Minecraft, it's a computer game that is based on voxel graphics, as you see over here. So pretty much everything in there is a block. It's very open-ended, so you can play the game in many, many different ways. You can go on adventures, you can play it socially to discover the world with friends. People build amazing structures. There's a concept that works like electricity called redstone. With that, people have constructed huge cities with complex transport systems. They have implemented computers, one transistor at a time, that actually work. So you can build a calculator within the game. So it's very fascinating for all those different reasons that it's, and in particular because it's so open-ended and so flexible. And exactly this flexibility and this open-endedness makes Minecraft such an exciting platform, such an exciting basis for AI experimentation. As I mentioned earlier, in AI research, the current open challenges are very much around how we can train agents that are flexible, that can solve different tasks and continue to learn as they go along. And exactly coupling the technology with a platform that is flexible, where you can pose very, very different problems and try to achieve very different tasks is very promising. Now, what Project Malmo provides is a very intuitive API for making AI experimentation in Minecraft as easy as possible. The platform provides embodiment, so an agent is put into this 3D world and experiences it like a human player, getting, for example, visual observations or other observations about the world, and they have to interact with the world and experience the consequences of their actions. So they learn from trial and error. They can learn socially, for example, from other players or other agents. And now with the platform, we also have full experimental control over the environment. So we can start with creating tasks for the AI agents that are easy enough so that current technologies can solve them. But as we go along and the technology becomes more powerful, we can start to create more and more challenging tasks to really push AI technology towards something that will eventually approach the kind of flexibility that we see in biological learning. To give you a very brief overview over the platform, essentially what it provides is a mod that already hooks into the game Minecraft, and it exposes the state of the world to the agent. It provides a reward signal. Then the platform would be used to implement an AI agent and would choose actions to send back to the platform. So this very much implements this interactive learning cycle that I mentioned earlier. The way this looks is roughly like this. What's important is that all the data, all the interactions with the environment are recorded and are available for learning. So here we can just see an agent walking around an environment. And we can see all the data that is recorded here. For example, the position of the agent, the visual input that it perceives. As I mentioned, this platform can be used to experiment with very different types of tasks. It also allows us to work with very different AI approaches. So it allows us to put on the same or roughly equivalent level something like the classic tabular Q-learning approach that I showed earlier, and something that works in a very different way, for example, using the visual input and deep learning to make sense of that particular scene. And we can start to very systematically compare those approaches to really further the state of the art in this research area. Just as an example here, the tasks in the platform are specified in a simple XML format where the experimenter can choose what kinds of observations the agent should perceive and how it interacts, what kinds of commands it can send to the environment. Just to give you an example, this is a complete agent written in Python in this case. So you would set up a particular mission or a particular task, put the agent in the environment, and then run it. Just to take this apart, the agent usually has this interactive cycle. This very much implements, again, the cycle that I showed earlier, where as long as the mission is running, you get some observation of the world state. For example, the reward, the current frames, or some other form of observation. You interpret this in some way and send a command back to the environment. So this is the simplest possible agent that you can start running. So this is just to illustrate that it's very, very easy to get started with this and explore new approaches to addressing some of those challenges. Just to show how cross-platform the Malmo platform is, this is the code that I showed in Python. That's the same code in Torch. That's the code in C++, Java, and C#. And don't worry if you haven't been able to read this as quickly, the point is that we have made the Malmo platform as cross-language and cross-platform as possible so that experimenters can go in and couple this with their favorite approach with systems or agents that may already exist in different programming languages and get up and running very, very quickly and start experimenting with the platform from day one. We're also very excited that the platform supports multi-agent interaction. So for example, you can imagine having an AI agent that has to solve a task collaboratively with another agent, or where you have agents compete against each other, or you could have interactions between a human and an AI agent, and for example, learn from each other, or understand how the agent can learn to effectively collaborate with the human player. So in summary, I talked about the current state of AI and highlighted that while there was dramatic progress over the past years, all current AI systems are still very much narrow. They are trained to do one particular task very, very well, but they have very little flexibility. They're not very robust to changes in the environment, and they cannot learn new tasks as you go along. They cannot generally become better as they practice a task over time. The challenge that we currently set out to solve is to develop flexible AI systems that can learn across tasks and learn new things as they go along. Project Malmo is providing the platform for that particular research. So it allows us to very easily set up new experiments, try out new technology, and hopefully work towards this very ambitious goal of flexible AI learning. I'm also very excited to announce that Project Malmo will be open sourced in the coming days. And you can already try the platform today in the demo that David Bignell will be giving in the afternoon. In the coming days, there will be an announcement about the open sourcing of the platform. So I invite you all to go and to try it out and give us feedback. Thank you very much for your attention.
Thank you very much, Katja. So we have time for a few questions, and yeah.
Are you planning to organize competitions and search for designing the best AI agent?
We've had a lot of discussions around that, and actually we've already worked with academic collaborators to get an idea of what would be best for the research community. I'm a bit worried that competitions usually don't bring out the best advance from the research side. So you usually get people to guard their particular implementation, their particular heuristics, and you don't really get a lot of collaboration towards actually solving a very ambitious goal. We are thinking about ways of, for example, crowdsourcing or collaboratively developing tasks and trying to move towards a more collaborative scenario where people can really collaborate on solving those very ambitious challenges. We have a few ideas around this, but if you have others, please come and talk to us during the demo session or after the talk.
Hi. Would you say that the problem with not generalizing different the AI not generalizing to different tasks is more a fact because Q learning is like learning a specific policy instead of learning something like a model of the world that you would do in other approaches?
Mm-hmm. That's a very good question. Part of it is related to simply the representation that tabular Q learning cannot learn new representations. And some of this is already alleviated with deep learning approaches to reinforcement learning. But I think you're right. A lot of the flexibility and generality in biological learning comes from model-based learning. We haven't seen a lot of work in that particular area, but it's something we're actively working on. It's a very exciting direction, absolutely.
Okay, if you want to do two more questions.
Of the last question, I mean, it doesn't seem like the real problem is like we need like, a more general motor inference for the environments. Mm-hmm. Like, I mean, you have also an AI on the environment, block that is also like adapting itself to the things that the agents are doing.
Mm-hmm.
because it seems, I mean, sometimes it seems for me like, I mean, the agent is doing something and the environment is already set up and react on the, or adapt, or, I mean, change the state on the environment, but the environment by itself is not, I mean, like learning itself, or we are not like learning something new about the environment. Seems like it's like more static instead of dynamic.
Right, right. So if I understand you right, you're worried about if we evaluate an AI approach or reinforcement learning approach in an environment that's static, we are not really modeling the real world. The real world changes all the time, and in the real world, we have to deal with that change. Because the environments in evaluation are typically static, we are not really addressing the full problem. Is that the problem you're mentioning? I think that's exactly right. And I think the only way to overcome this problem fundamentally is to have humans in the loop. So initially, we can still push a lot, we can still do a lot of research in improving AI approaches in a reasonably static environment, because there's still so many open questions around generalization and adapting to new tasks. But eventually, the real test will be when an AI agent has to interact with a human, with a person whose tastes change over time, who may give different feedback, very different instructions on different days, who may be, in a different mood, et cetera, et cetera. So I think a lot of dynamicism will come from interaction with humans. And I think the core AI challenge is to actually learn effectively in a setting that is that dynamic and that has humans in it. Yeah.
Okay, we'll have one more question. Yeah.
Continuing the theme about learning from very few examples and things like that, what potential do you see, for example, for an unsupervised learning? Because actually Jeff Hinton once said that actually people don't learn to recognize objects the way ConvNets do it. So they are not provided with thousands of examples of birds and saying this is the bird and this is the car and this. They only just maybe told once, and they try to generalize and to build a proper model by themselves. So.
Mm-hmm. Absolutely. I think there are many very interesting threads that you mentioned there. One point that I would like to counter a little bit is this lack of experience or lack of data that is typically mentioned. So an actual child growing up is seeing millions and millions of images, is hearing a million words, by the time they're 3. So there is actually a lot of data that they can learn from. But I very much agree, a lot of that is not in this very nice format of this is a bird, this is an apple, et cetera, et cetera. But there is a lot of unsupervised learning, potentially model learning, as you mentioned up there. And eventually a learning step is really just attaching, for example, labels to a particular concept that intuitively an agent or a person already understands. It's not quite clear yet how to achieve that kind of model in an artificial agent, but I think that, again, that's a very interesting direction for research.
Okay, I think we'll wrap up here, and because there'll be more opportunity to ask questions in the demo session this afternoon.